All right, so now for something new, different. As Hannah mentioned, Heather mentioned, I'm Ryan Elias. I'm a food chemist. We do work in my lab in food stability mostly, which really means the chemistry of food shelf life, more or less. Okay. And today what I want to do is a couple things. I want to just give you guys some background of the problem. Really the problem with oil stability is not a microbiological one. It's not like it's a product that's really susceptible to bacterial spoilage, yeast, molds, so much. It's really a chemical thing. It's a chemical stability issue. Okay, so I'll talk about that. And I want to also hand out some oils too. We have some examples of some refined and unrefined oils, and some sensory standards too. Okay, and I'll explain what that is and why that's important later. Okay, and again, please let me know if you have any questions throughout here. I'm going to try to spare you a lot of the chemistry here, but it's hard to talk about this without a little bit of chemistry. So a couple definitions here. The word lipid is probably a word you've heard of, and it's kind of a big category. But what we care about really in this context are two things: fatty acids. Okay, so it's just sort of a long chain. It's a hydrocarbon chain. Okay, more about that later. And then triglycerides. You've heard of all these, right? Yeah. Okay. A triglyceride essentially is just three of these things stuck together onto a glycerol molecule. Okay. Other lipids in foods, cholesterol, that's important, phospholipids. We don't care about cholesterol in oilseeds because you need a liver to make cholesterol, and plants don't have livers, as far as I know. Waxes, etc. But this is really the category that we care about, these two things right here. Okay. So I'm going to use canola as sort of the example today. Okay. Although what I'm talking about also has relevance to sunflower oil, other oil seeds, olive oil even. Okay. When you press off some canola oil, what you collect there is really mostly triglycerides. Okay, it's mostly these things right here, about 98, 99%. Okay. Within that broader category, we have different types of fatty acids. Okay, we can have different types of these constituent fatty acids. Some can be saturated. I'll talk about what that means in a bit. Or unsaturated. You probably heard these terms too. Okay, but basically that's the category. And then there's this other stuff here too, this 1%, which seems like it'd be trivial. Like, who cares about 1%? But this 1% affects everything. It affects the color, the flavor, the aroma, the susceptibility to oxidation. All those things, okay? And refining is really about dealing with this stuff, this other stuff, okay? Getting back to this saturated, unsaturated question here, we know one of these is supposed to be better for us and one's not so good for us. We've been told for decades now that saturated fatty acids are good for us in the diet. Unsaturated fatty acids are bad. There's probably some truth to that, but it's a bit more complicated, I think. But basically, a saturated fatty acid is one where you've got single bonds linking all of these carbons together, right? Okay. If you've got a double bond, at least just one double bond, that's an unsaturated fatty acid. If you've got one, it's a monounsaturated. If you've got more than one, it's a polyunsaturated. Okay. What is significant here, at least for you guys, and for me in my lab, is that these ones are the ones that are susceptible to oxidation. These are the ones that can spoil, that can go rancid. These things are inert, essentially, okay? Which is kind of a pain for a food manufacturer. We'd really prefer to be dealing with these guys right here because we have a more stable product. But the demand for these is higher because of health benefits, and also some functionality too. These things tend to be solid at room temperature. Okay, these are fats. So a lipid that's a solid at room temperature is a fat. If it's a liquid, it's an oil. All right. So these things are fats. These are oils, and you don't always want to have fats. Sometimes, like a salad dressing, you need something that can flow. Okay, so you need a liquid oil. But the trade-off there is stability. oxidation, as I'll talk about. So this is the big term here, rancidity, okay, a rancid oil. You guys have heard this before. Everyone's heard this. I want to define what that really means. The category is split into two, okay? Hydrolysis or hydrolytic rancidity means something very specific. It means something, a reaction that causes this triglyceride to be cleaved and to fall off that backbone. Okay, so you've got 3 fatty acids here, a glycerol. A hydrolytic rancidity reaction would cause this thing to get kicked off. Okay. Why does that matter? Well, you actually can't smell this often, at least with oilseed fatty acids. You can taste them. They taste soapy, essentially. So it's an off flavor. Okay. We'll talk about how this happens in a bit. The other reaction that's important here too is oxidation, or oxidative rancidity. And that's a very different thing, and actually a much more complicated thing too. Unlike this reaction gives you a whole slew of products. And some of these products are really small, these little aldehydes, if that matters to you, that get kicked off, broken. This is a free radical reaction. And then these things actually can smell. They can partition to the gas phase. We can perceive them. We can smell them. We can taste them. And they don't taste good. Okay. We're sort of biologically tuned to this stuff. You know, if you smell this stuff, it means there's something bad with the food. So we're sort of programmed to reject these kind of products. Okay. Dealing with hydrolysis. This, I think, is an issue with unrefined or minimally refined oils. I think it's a problem probably in this room. Maybe you don't know it yet, but it really is. Whether or not it matters or whether or not you can taste it in your final product, it's a different matter. But I guarantee there's probably some hydrolysis going on in your process, especially if you're not preheating your seeds or if you're doing cold pressing. Because the reality is that this reaction happens by an enzyme that's already in the plant, okay, in the seed. And if that enzyme is active, it can cause that reaction, you know, upon pressing. Okay. So you can prevent their formations. That's one approach, and I'll talk about how to do that. Or you can actually remove those products as well, and that's called neutralization. You might have heard this as well. Okay. I'm not sure any of these things make sense to people doing what you're doing. All right, so you can prevent them, or you can remove them. You know, this probably is a bit trickier to do, I would guess, but in any case, I'm not convinced it's a problem yet. Okay. The real issue, I think, is oxidation, is this oxidative rancidity. And that is, again, something that requires an unsaturated fat, so those double bonds, and you need some catalyst. There's some requirements to that reaction. And you don't need much to really cause some kind of sensory effect. You know, you can smell these oxidation products at very low concentrations. It's a problem. Okay.
Go back one slide, please. Just under number 1, those 2 bullets seem to be at odds.
Oh yeah, sure. Okay, so the reaction that is important, at least in non-fryer oil, okay, oil that you're pressing off, is enzymatic hydrolysis, an enzyme that goes in and cleaves this bond right here to give you this. It's kind of lipase is the enzyme. You can denature that. You can destroy that enzyme with heat. If you're doing cold pressing, that heat is not high enough. You need about 200 degrees Fahrenheit to denature this enzyme. Okay. But you could preheat your seeds beforehand. That's a possibility. Or you can denature the lipase after the fact. The definition of cold press, I think, Doug and I were just talking about this before, really has to do with the process itself, the actual mechanical, the pressing of it. If you're pressing it cold and the max temperature is 120, right, Doug? If you're within that range, that's okay. If you're above that, it's not cold press. I don't know of any reg or whatever that says you can't preheat a seed before you get to that point to denature that enzyme. It's something we can look into. But on a commercial scale, this is a pretty important step, and almost everyone does it. They'll preheat their seeds. Actually, they'll do 2 preheating steps. They'll preheat it at a more mild temperature just to get the oil flowing. It makes seed shattering less of a problem and increases your yield. That's one reason. And then a second step they'll do after they flake or roll out the seeds to denature lipase. Okay.
So to keep things cool part, is that the finished product?
Yeah, that's if you're not going to preheat here, you can keep things cool just to slow down the enzymatic reaction, just to slow it down. On a big scale, they're going to try to prevent this from happening by preheating, or they're going to just not worry about it and just neutralize later. Okay, but these are all very big processes. Rancidity, this oxidative rancidity is a big problem, as I mentioned, and it's a lot harder to control in a product like what you've got. The catalysts are metals. These are transition metals, things like copper, iron. Iron's the big one in a processing setting. You can't really control these things. They're just environmentally, they're ubiquitous. They're there. You just have to sort of minimize that or just be aware of it. Some requirements for that to happen, as I mentioned, you need to have this unsaturated fatty acid. You need that as the substrate. If you've got a saturated fat, it doesn't work. So you've got to have something like this in oil. Canola's got lots of unsaturated fatty acid in it. It's got mostly oleic acid, which is a monounsaturated, but there's some omega-3s even too. So those are prime candidates for oxidation. Okay. So in industry, how do we deal with this? Well, we can just hydrogenate it. We just bubble in hydrogen gas, and you can saturate all those bonds and convert chemically a unsaturated to a saturate. That's fine. You get something that looks very different, right? Because now you're causing that saturation to occur, and you're making the room temp. You're making the melting point change, and you're essentially changing oil into a fat. So this is Crisco. I mean, Crisco is just soybean oil that's just been hydrogenated. Okay. There's some health implications with this. You know what I'm talking about? Probably the biggest issue is the trans fat issue. So these trans fats, I'm not going to get into what that means really, but that's a byproduct of this reaction. And you're converting healthy unsaturates to saturates. But this is, for a lot of food applications, desirable for a formulation from the processor's perspective. So that's one way of doing it, and that's pretty common, although it's getting less common, hydrogenation. You can scavenge the free radicals. This reaction is all mediated, promoted by free radicals in the food, in the oil. So you can scavenge these things with antioxidants. That works really well in formulated foods, things like dispersions, things like mayonnaise and dressings, and things where you've got some water there, because most of these antioxidants that are most effective are really water soluble. There's a few that we can add to lipids that are lipid soluble, but really what we're talking about is food dispersions, lipid emulsions, things like that. So an antioxidant works. You might have seen these things on labels, right? Well, tocopherol is vitamin E. That's a pretty consumer-friendly one. This one, BHT, is a really good antioxidant. You see this in a lot of foods. It looks horrible on labels. Consumers don't like it, and it probably causes cancer at certain rates. So we try to avoid that. There's other ones too, TBHQ. As food chemists, we know exactly how to stop this. It's just a matter of can we put it in a food and not kill people. That's the challenge for us. Will people accept it? UV light is also a problem. This is a catalyst for this reaction too. Okay, so this is something that can cause the production of these free radicals to begin with. So packaging is often an important consideration. You'll notice in very high-end extra virgin olive oils, what color is the bottle? Is it clear? It's not clear ever. No. Often the producer would love to make it clear because you can see the color of the beautiful oil, but it's usually brown or dark to keep light out. And there's something similar, although it's a different reaction altogether, that happens in beer as well. So good beers, in my opinion, often have dark brown glass that really shields the product from the light. There are some companies that have workarounds, or if you're Corona, you just tell people to put a lime in it to cover up the smell of the issue, just cover it up. But it is also an issue in oil seeds too. And actually, Doug and I are working on a project right now that looks at packaging, that looks at the color of packaging on these unrefined oils in terms of oxidative stability. Okay, so it's probably an issue for us too. High temperatures should be avoided as well. That's sort of intuitive. You know, you raise the temperature of the environment, you increase reaction rates. That happens with oxidation, this oxidative rancidity, as well as hydrolytic rancidity. So it's often good to keep your oils at kind of a low temperature. You can prevent exposure to oxygen too. Sure.
How low go?
Well, you could freeze an oil, really. You just have to thaw it later. I mean, in my lab, we do a lot of work in marine oils, fish oils and algae oils. And we keep them at minus 80 C. We keep it cold. When we need it, we pull it out, and it thaws.
No effect on that product?
No, none, no. I mean, it's not a complex food. There's no structural changes. It's just freeze thawing. It's just expensive to freeze large volumes of oil, you know, or keep it really cold. So it's sort of an economic decision, I guess. Oxygen is sort of the fuel for this whole thing. It's oxidation. It's in the name. You need oxygen. So how do you prevent this? Well, a great way of doing this is preventing oxygen exposure. It's a really good thing. Seems intuitive, right? But can be tricky, especially since the solubility of oxygen in oil is very high compared to water. Okay, so water can only solubilize so much oxygen. Oil can solubilize about 8 times as much, so it likes to be in there. If you've got a food product that's amenable to it, you can vacuum pack. You know, if you've got you know, a lipid-based food, a meat-based food, you can vacuum pack, pull out that oxygen. I don't think that really makes sense for what you guys are doing here. What probably makes more sense is using inert gases in your production. Okay, so nitrogen is a tank of liquid nitrogen or gaseous nitrogen. It's pretty cheap. You know, it doesn't have to be very high purity, and you can use that to blanket things. Argon's even better because it's heavier than nitrogen. So you know, you put a nice blanket on top of a barrel or something like that. So inert gases are often used in industry. We use this in the food industry all the time for this reason. So it's something to consider. Even CO2 could work here too. So I think oxygen exclusion is probably a tool that is good for you guys. I think it would make more sense than having to think about different antioxidants you could add. I think you want to stay away from that. There's some regulatory issues there as well, whereas gas there's no such issues, and it's probably just as efficacious. Chelators is another category. As I mentioned, these transition metals, iron, copper, these things catalyze these reactions. You can't feasibly remove these things from a food, from the environment. You just have to accept that they're there, and then either ignore it or do something about it. And if you've got a formulated dispersion, if you've got something like a salad dressing, you might add something that will bind up those metals. So you'll see this on a lot of labels. EDTA, you guys have seen this? EDTA. It really, really strongly binds iron and copper to some extent. It prevents them from catalyzing reactions, these oxidation reactions. The problem is, at least for a bulk oil, you know, like we're talking about, these things are not very lipid soluble. They need to be solubilized in water, so it's kind of a problem. You know, if you're going to be making some foods, some products out of your oils, it's something you could consider. You know. So here are 2 labels. It's probably tough for you guys to see this, but here's mayonnaise, and you'll see there's tocopherol and there's EDTA in this thing. So it's sort of a two-pronged approach to it, which is pretty common in the food industry. Here's another label with TBHQ, another antioxidant. I don't think you want to get into this. Okay.
There's a level of vitamin E in a lot of these oils. So is it actually going to help in the oxidation process, or is there enough in the oil to even help that?
The tocopherol that's present in the oil is very important in terms of protecting it. And you lose a lot of that with refining, for sure. I'll talk about this in a bit, but it's really this sort of competition between these antioxidant factors. Tocopherol is a great antioxidant, and pro-oxidant factors. When you refine, you get rid of all those things. So, you're just like, well, and that's the question. That was part of our research. We wanted to know, well, the conventional wisdom is refining promotes longer shelf life. And that's why people do it. They're not doing it just because it's fun. It's a pain, really. But in a lot of cases, you're removing those pro-oxidant factors. And you can add back tocopherol. A company can do this. But at least from our studies, that endogenous tocopherol that's there from the beginning is pretty important. Okay? If you can save that, it's good.